Now we have these equations, and these equations is about the speed of the galaxy. So if you look at the top, uh, this is the change in the wavelength. So at the top, you have the change in the wavelength divided by the wavelength in the lab. So this is the one in the lab, and here you're doing the difference. And this is the speed of the galaxy, and this is the speed of light. That's 3 times 10 to the power of 8. So the change in the wavelength divided by the wavelength in the lab is equal to the speed of the galaxy divided by the speed of light. You can also do the change in the frequency divided by frequency equals the speed of the galaxy divided by the speed of light. Okay, so here we have a question. Let me read out the question. So the diagram shows some of the energy levels of the electron in a hydrogen atom. Now, if you look at the scale, so here you have energy and you got 10 to the minus 19 joules, right? Just be careful of the scale. And it says show that the wavelength of the photon produced is about 410 nanometers, and it's going from X to Y. Okay, so I've drawn another diagram. I've drawn another diagram where the electron is going. It's going from X to Y, and we've got minus 5.42 take away minus 0.58. Okay, and it's minus minus, so that makes plus. Uh, this line is the magnitude, right? So when you do minus 5.42 minus minus 0.58, you end up with 4.84 times 10 to the minus 19 joules. We're using the equation E equals HF, but also E is equal to hc over lambda, right? We want to work out the wavelength. So your E, which is this is your E, that's your E, E equals hc over lambda. Rearrange for lambda, and you should get 410 nanometers, right? So this is your energy, this is your H, this is your C, and then rearrange for lambda. Okay, so I'm just going to read out the question. Here it says, explain the origin of the dark lines. So the answer is that the dark lines is caused by the electrons absorbing the incoming light. The other wavelengths just pass through the atom. The electrons go to a higher energy level, and this is caused by the light going through stellar atmosphere. Okay, I'm going back to this slide because in the next question we need to work out the speed of the galaxy, and here we need to know that the wavelength of the photon is 410 nanometers. Okay, so we're doing 400. So here we have the change in the wavelength over the wavelength, which is this one here, and that is equal to V over C. So we're going to do take away. We're going to do 432 minus 410. This is 432 minus 410, and then we're going to divide by the wavelength in the lab. So 410 is the one in the lab, and then we're going to times that by 3 times 10 to the 8, and then you should get 1.6 times 10 to the 7 meters per second. Okay, you need to recognize the HR diagram. So on the scale, it's usually 10 to the 4, right? 10 squared, 1, 10 to the minus 2. But here they've just logged it. So on this side, LG means log to the base 10. This is your main sequence, right? This is your main sequence. Here you have your white dwarfs. Here you have the supergiants, and then here you have the giants. And then don't forget that the temperature is going backwards, right? So here the temperature is, when I say backwards, I mean the temperature is increasing from left to right. Okay, so now let's move on to this question. Use figure 21.1 to show that the surface temperature of New Persei is about 6,300 Kelvin. Now let's read out the question. So this is just talking about the sun. So that the sun has that temperature and the wavelength is at here. So we need to put that into an equation. So this is your equation. Lambda is equal to k over t. Let's work out the constant. So k is lambda times t. K is lambda times t. And so your t is 5,800. And your wavelength is 500 nanometers, yeah? So your t is 5,800 and your wavelength is 500 nanometers. Your constant is this. So this is your constant. Using that constant, we're going to put it into here because we want to work out the surface temperature. So T is equal to K divided by 470. Now you get the 470 because you look at the graph. So this is the peak and you go down. Unfortunately, I don't have a ruler here, but this is the maximum value is 470 nanometers. And then we want to work out T. Because we know that K is this, just put that into the equation, and then you should get I got 6,170, but that is the maximum value, right? So this value should be smaller than 470, but you should get 6,300. Okay, and then now it says to estimate the radius of New Persei. Okay, so um, the temperature we've worked out was about 6,300. This is your equation. Luminosity is 4 pi r squared sigma t to the power 4. We want the radius. So rearranging for the radius, r is equal to the square root of L divided by 4 pi sigma t to the power 4. And then you put all the numbers in and you get 1.4 times 10 to the 10 meters. Okay, other questions that you may need to know is that the Young modulus is stress over strain. And remember that stress is force over area. So stress is force over area. And the strain is the extension divided by the original length. You can put them all into one equation, right? So this is the Young's modulus. This is stress and this is strain. So when you're doing stress divided by strain, you get force times original length divided by area times extension.